So the plan today is that I'm going to talk about a little bit of my thesis work and kind of one chapter of my thesis. And this is joint work with Carlos Amendola and my one of my thesis advisors, Jose Rodriguez. And this talk kind of maybe more broadly, it can give you a sense of what a problem in this field known as algebraic statistics looks like. So it's an area of applied algebra that uses techniques from algebra and kind of specifically algebraic geometry to tackle problems in statistics. So, anytime you're kind of working at the intersection of two fields, I think there's kind of room for additional maybe confusion. So please stop me at any point if anyone has any questions. So we can get going here. So to begin, I will kind of set up the problem that we're interested in, and then we'll talk about some techniques from algebraic geometry that will be useful to us. And then at the end, I'll get into kind of more of our results. So, okay, to begin, a very classical problem in statistics is what's known as density estimation. So formally, what this asks is, suppose I give you n samples from some unknown distribution P. Can we estimate what this distribution is, or the density of this distribution? Well, really, in order to have any hope of solving this problem, we need to assume that P lies in some family of distributions. And this is information that's, kind of a priori you may not have if you're just given, say, a bunch of data. But the following family of densities is a good choice because of the following theorem. So the following theorem tells us that a Gaussian mixture model is a universal approximator of densities in the sense that any smooth density can be approximated arbitrarily well with a Gaussian mixture model, so long as it has enough components. So what this tells us from a practical standpoint is like, okay, I give you a bunch of data, and maybe the data doesn't, come from a Gaussian mixture model, but it's kind of good enough for all intents and purposes because a Gaussian mixture model can approximate the data, arbitrarily well. Okay, so this really motivates our study of density estimation for these Gaussian mixture models. So, okay, just to kind of be completely on the same page, I'm sure this isn't a surprise to anyone here, but we say a Gaussian random variable, a random variable is a Gaussian random variable if it has this following exponential density. Then a Gaussian mixture model is a random variable that is a convex combination of k Gaussian densities. So on the left here, we'd see a picture of, standard the density for a standard normal 0, 1 random variable. And then on the right, we see a mixture of two Gaussian densities. So kind of off the bat, you can see how much more expressive these Gaussian mixture models can be. For instance, this density is bimodal, it's not symmetric. And so, maybe you can believe that, this only has two components, but as I add more components, that I can kind of approximate all sorts of behavior. So kind of putting a problem into the context of these Gaussian mixture models, what we assume, we're given n IID samples, y1 to y big N, and I assume that I know it's distributed as the mixture of k Gaussian density. So I'm going to assume that I know the number of components. Then the question now is, how do I recover the mean, the variance, and the mixing coefficient of each Gaussian component? Well, if you've taken some, statistics classes, the first idea that might come to mind is to do maximum likelihood estimation. So maximum likelihood estimation is this optimization problem kind of pictured here in this context that's very prevalent in statistics and very well studied. And it's an aptly named optimization program in the sense that it really seeks to maximize the likelihood that your data came from a given Gaussian density. Now, as long as k is greater than 1, so as long as we're in the situation where it's a mixture of two or more Gaussians, maybe you can kind of see, or at least believe me, that this objective function here is non-convex. So off the bat, we can only hope for any kind of local information. And there does exist an algorithm, it's known as the EM algorithm, that will, will find some local critical points. And this is very well used in practice. But there's some issues. So the first one is that these local optima can be arbitrarily bad with respect to this likelihood function. And moreover, random initialization will converge to these bad points with high probability. In addition, it's been shown that there's no sample size independent bound on the number of critical points. So what this means is, sometimes in some of these optimization problems, if there's only, a small number of critical points, maybe you can find them all, kind of enumerate them all, and then select the best one. But unfortunately, that's is not the case with this problem. In addition, you need to access the samples, or all samples at each iteration of this algorithm. And so if you have a very large data set, this can be computationally prohibitive. So kind of this whole slide, all of this to say is that maximum likelihood estimation, it's kind of very popular, and in many setups, it's kind of a very nice technique to use. But for these Gaussian mixture models, it's kind of a priori, we know we're kind of guaranteed no useful statistical guarantees from what this outputs. Okay, so that means we want to use something else. So the second idea is to use another classical technique, which is known as the method of moments. Now, one nice thing is that this method of moments estimator is consistent. So that means that as my sample size tends to infinity, I'm guaranteed to recover the true underlying density. In addition, it's been shown, and I'll touch on this in a bit more detail in a bit, that these Gaussian mixture models are identifiable from their moments. This means that, if I kind of run this method of moments procedure, I actually am guaranteed to recover the true Gaussian density. So this is the kind of key of this work. It's this big if. If you can solve the moment equations, then actually kind of a priori we're guaranteed that we can recover the exact parameters of our underlying distribution. So kind of for these reasons, this talk and this work really focuses on doing the method of moments for these Gaussian mixture models and trying to make them more computationally tractable. Okay, so what is the method of moments? Well, if I give you a random variable x and it has density f, then I define its ith moment as the expected value of the random variable raised to the ith power. A key feature of moments is that for parameterized distributions, moments are actually functions of the parameters. So for instance, if I give you a normal mu sigma squared random variable, then its first few moments, you can see here are functions, specifically polynomial functions, of the unknown parameters mu and sigma squared. So the method of moments exploits this, and it works as follows. So I consider a statistical model with p unknown parameters, which I'm going to call theta 1 to theta p. Then I consider the moments up to order big M as a function of these parameters. Step 1 is to take my samples and compute the sample moments. And then step 2 is to solve this system of equations, set the sample moments equal to the moment equations to recover the parameters. So kind of for a context of Gaussian mixture models, the first step is to understand these moment equations. Well, the moments of just Gaussian random variables can be calculated recursively. Then the moments of mixtures of Gaussian random variables are just convex combinations of the moments of each kind of Gaussian component. So, I know looking at this slide is probably not clear at all what these moments look like. So, kind of like a lot of things in math, it's easiest to start, the simplest case and sort of build ourselves up. So let's start kind of in the most trivial case. This is when k equals 1. Well, okay, we really don't have a Gaussian mixture model here, right? We're just doing density estimation for a Gaussian random variable. But, either way, in this case, we can write out these moment equations. And then you can see this is actually a triangular system. So kind of using maybe high school algebra, you can back solve for each parameter. And in this case, you see that there's a unique solution given as follows. Okay, not so exciting, but, maybe at least it's good to check that this procedure works in the simplest case. So now let's look at maybe the first non-trivial case, and this is when k equals 2. So in k equals 2, I can write out the first 6 moment equations. And you can see here I've got 6 moment equations in my 6 unknown parameters, which is lambda 1, lambda 2, mu 1, mu 2, sigma 1 squared, sigma 2 squared. Now, the first thing to observe in this case is that we have some symmetry in this system of equations. Namely, if lambda 1, mu 1, sigma 1 squared, lambda 2, mu 2, sigma 2 squared is a solution, so is the solution that happens if I just permute the indices. So this type of symmetry is kind of very well documented and studied in the statistics literature, and it's known as label swapping. So kind of what this tells us is that for a k mixture model, we know solutions are always going to come in groups of k factorial, right? So we have this action of the symmetric group. And so, off the bat, we're just hoping to identify our parameters up to the action of this symmetric group, which kind of for all practical purposes doesn't, it doesn't matter, right? Because it doesn't matter if you kind of the order you list the Gaussian components is what this says. The second thing is that actually this k equals 2 case kind of is what's maybe considered to some the start of this method of moments idea. So the study of the mixture of 2 Gaussians actually dates back to Carl Pearson in the late 1800s. And he was studying measurements of Naples crab populations. So essentially, he was collecting these crabs. He was measuring the body length and the body width, and then recording this ratio. And then I guess, hopefully throwing the crabs back. And as he did this and he collected his data, he got this following histogram of data. And what he observed is that this didn't look quite Gaussian, right? It's a little bit skewed to the right. And so what he conjectured is that he actually wasn't observing a single population of Naples crabs, but there were actually 2 separate subpopulations that he was observing. So he proposed using the method of moment to then recover the parameters of the individual kind of subpopulations. So what he did is he, took this polynomial system here and plugged in M1 through M5, which he got as sample moments from this data. And kind of predating any sort of Grosvenor basis theory or elimination theory, and definitely predating any sort of computer algebra software, I should say, he was able to reduce solving this polynomial system to finding the roots of a degree 9 polynomial in this variable mu1 times mu2. So this is something that kind of modernly we would probably call an eliminant, but he kind of did this, before any of this kind of language appeared. Another thing to note is that he broke the symmetry. He broke this label swapping symmetry by essentially projecting onto this variable mu1 times mu2. And once he kind of reduced his problem to solving this degree 9 polynomial, he was then able to back solve to find the other parameters that he needed. And so kind of most importantly from this example to see is that he set up this nice framework. So namely what he did is he took, in this case, we have 3K unknowns. And so he took the first 3K moment equations. He solved the square polynomial system to get finitely many potential densities. And then he selected the statistically meaningful density, which is closest to the next sample moment. And so this is the framework that we would also like to follow. But there's kind of quite a bit of details that need to be addressed, right? So for instance, the first statement here, solve the square polynomial system to get finitely many potential densities. Well, if we've taken any algebraic geometry, honestly, even linear algebra, right? We know that just because you have a square system of equations, that doesn't mean that you have, a 0-dimensional variety, right? So this is kind of one important detail that needs to be resolved. Then the second one is this select, once I have my finitely many densities, select the density that is closest to the next sample moment. Well, this is a question of identifiability. And again, it's not clear that this is the case. So, before we can kind of get started at any of kind of going on this framework, there's some details that need to be resolved. And I claim that these are all details that can be framed under the idea of identifiability. So there's different notions of identifiability, but they can all be framed in terms of the fiber of the following map. So this map works as follows. So I take my mixing coefficients, my means, and my sigma squared. So I take, essentially all possible parameters corresponding to a Gaussian K mixture model, and I map them through the moment equations M0 to M sub big M. And then what I do is I look at a fiber above a point in this image. So the first notion of identifiability has to do with the first sentence of the last statement, which said, we solve a square polynomial system and we get finitely many densities. So this can be framed as a statement of algebraic identifiability. And what algebraic identifiability asks is, how many moment equations do you need such that if you take a generic point in the fiber and you look at if you take a generic point in the image and you look at the fiber above that point, then how many moments do you need such that there's only finitely many points in this fiber? Now, kind of just a naive parameter count tells us that we should need the first 3k minus 1 moments. This is because we zero index, right? So we have 3k unknowns, so really this is 3k moments. And it's actually been shown in 2018 that this is enough. So we know we need at least 3k minus 1 moments to get down to finitely many solutions. And actually, generically, this will be exactly how many you need. Okay, so that's good. This really resolves the first statement. Now, the next statement is a little bit trickier, and this is one that says it's a question of kind of strict identifiability, or what we call statistical identifiability. And what this asks is, for what order moment will a fiber for every single point in the image of this map, will the fiber equal exactly k factorial? Now, this k factorial, remember, this is that label swapping symmetry. So really, this is just a unique density up to that sk action. Notice here, this detail, this is for all. So we kind of dropped this generic assumption, and we really want to know for every single possible point in this image, what order moment do we need to go up to so that this fiber consists of kind of 1 point up to this label swapping symmetry. And in 2012, this was resolved, and it was shown that if you take the first 4k minus 2 moments, that you need that each fiber will have exactly k factorial points. Moreover, they show that there exist Gaussian densities that are only identifiable, or that are not identifiable using moments of order less than 4k minus 2. So really, this bound is sharp. But this for all assumption is actually pretty strict. And so, kind of in practice, what we're doing is we're using samples. So there's some notion of randomness in there. And so what we'd like is something that bridges 1 and 2. So this genericity assumption of this top equation is actually it's actually not a big assumption, right? Because kind of with probability 1, you'll lie off a Zariski closed set in the image. So the first result I want to present is something that bridges the notions of identifiability between algebraic and statistical, and this is called rational. And what this asks is, what order moment do we need to go up to such that for a generic point in the image, a fiber above that generic point is equal to k factorial, which again is just 1 up to this label swapping symmetry. And the first result that we were able to show says that mixtures of k univariate Gaussians are rationally identifiable using moments up to order 3k plus 2. So now, we think that, because again, we have 3k 3K unknowns. So you might think, moments M0 to M3K are enough to kind of rationally identify for rational identifiability. And this is what we conjecture is actually true. So we think that this 3K plus 2 could be knocked down to 3K, but at least for now, this is kind of the best bound that we have for rational identifiability. So, okay, I know this is like, this slide it's a little bit wordy on my end, and I know it maybe, if you don't think of these notions of identifiability a lot, it can be kind of confusing. So I can maybe stop if anyone has any questions on this. Okay. Otherwise, yes, I'm happy to move on. Okay. So kind of the most important thing that we should take away from this slide, if we don't want to kind of get caught in all these details, is that this general framework that I mentioned here of, we have 3K unknowns. So we use moments M0 to M3K minus 1 to solve this square polynomial system to get finitely many densities, and then select the one closest to the next sample moment. This framework is actually mathematically solved. That's kind of the key takeaway here, is kind of all the little things that we imagine can go wrong actually don't in this case. Okay, so let's kind of write this out. So how we proceed with the method of moments here is we take our moment equations M0 to M3K minus 1, and we solve these moment equations over the complex numbers to get finitely many complex solutions. So the reason we do this is that over the complex numbers, the number of complex solutions is generically constant. So if we find them all, then we kind of know so essentially, like, there's a way that we can find them all, is kind of the point. But from there, because this is, we only care about these statistically meaningful solutions, so we filter out the statistically meaningful solutions. So these are real valued solutions with positive mixing coefficient and positive variance. Once we have this kind of smaller set of solutions, we then select the statistically meaningful solution that agrees with the 3K plus first and 3K plus second moments. And so long as we use exact moments, so not sample moments, but like the true moments of a Gaussian density, then we're guaranteed that this procedure will exactly work. So the main kind of point of this work and the main kind of takeaway I want you to get from this talk is that this first step, this is kind of the computational bottleneck in this whole procedure. So really, how, if I give you a square system of polynomial equations, how do you find all of the complex solutions in some kind of efficient way? So really, we can reduce this to say, how do I solve, a square system of polynomial equations? So before I get into, kind of doing this for our specific problem, I think it's worth looking at some kind of general methods one can use to do this. So for this, I think it's kind of worth going through some kind of, general methods in numerical algebraic geometry. But again, maybe now again is a good point to stop if anyone has any questions about our problem setup or kind of approach.
Can you maybe recall just briefly actually what you meant by almost all moments in the image?
Yeah, so what this is so this notion of genericity we use a lot in algebraic geometry. So formally what it means is that for any moments in a Zariski open set in the image, but a Zariski, a non-trivial Zariski open set, let me say that. So a non-trivial Zariski closed set, that's going to be the zero set of a system of polynomial equations. So this is necessarily of lower dimension in the image. So the reason that this is kind of a very loose assumption is that, with probability 1, you're never going to land on this lower dimensional hypersurface or this lower dimensional variety in the image. And so, yeah, I guess formally that's what we mean.
And the algorithm that you described, where you stop first on the first step at 3K minus 1, was because you want to first check the algebraic step, and then you want to move to the rational
Yeah,
identifiability.
that's right. It's because once we're at this step, like this finite number of complex solutions, we know it's generically constant. And so we have a number, which means if we get, that number of complex solutions, we kind of know we've gotten them all, and then we can proceed. And, I'll kind of talk about some of these general methods to solving these polynomial systems. A major thing is that actually there's no good way to handle overdetermined polynomial systems right now. The only way to do it is to kind of square them up by taking a random linear combination, but then you're kind of back in this setup anyways.
Okay, thank you.
Mm-hmm. I see one question in the chat. Yeah, non-trivial Zariski closed set. So this is so the Zariski topology is kind of really well studied in algebraic geometry, and so the Zariski topology is one where the closed sets are defined as the zeros, the set of zeros of a system of polynomial equations. So essentially, the closed sets are algebraic varieties. Then the open sets are the complements of algebraic geometry, of algebraic varieties. And so, maybe you can just even think kind of affinely in 2 dimensions. The zero set of any kind of polynomial equation is going to be lower dimensional than the ambient 2-dimensional space. And so, like, even over the complex numbers. And so this kind of word generic pops up a lot in algebraic geometry and applied algebraic geometry. And it's kind of really considered a very minor assumption because of this reason, because it's some kind of lower dimensional object that you need to avoid, and with probability 1, you will avoid it. Great. Okay. But with that, maybe I can kind of continue on and give a little bit background on some techniques from numerical algebraic geometry. Okay, so just to kind of make sure we're all on the same page, if I give you a set of polynomials with real valued coefficients, well, I define the complex variety of the system as the set of common zeros. We, in this talk, are interested in the case when the number of equations equals the number of variables, and they form a complete intersection, meaning that you get finitely many solutions. So I tell you, essentially, we can kind of think of this a little bit more simplistically. I tell you, I've got some set, and there's finitely many elements in this set. The first question you might want to ask is, okay, how big is this set? Well, this is, again, a very classical question asked, and it was actually resolved by Bezout. And what he showed is that this variety is bounded above by the product of the degrees of the polynomials. So for instance, if I have a system of 2 equations in 2 unknowns, and they're both degree 2, then what Bezout's theorem tells me is that either I have, some infinitely many solutions, or some positive dimensional component, or I have less than 4 solutions over the complex numbers. Moreover, this bound is actually, again, generically tight. So kind of generic, meaning if I have a system of polynomials of certain degree and it's full monomial support, and then each coefficient is kind of random. So, take a kind of a generic quadratic polynomial where you kind of fix the monomial support to have support, 1, comma x, comma y, comma x squared, comma y squared, comma xy, and draw a random coefficient, say from a normal 0, 1 distribution, or pretty much any kind of continuous distribution. Then actually you'll, with probability 1, get exactly the Bezout bound many solutions. Now, the issue here, and maybe you can kind of recall from the slides that showed the moment equations, is that our polynomials aren't generic in this sense. Specifically, they're sparse. So kind of a priori, some of these moment equations, the ith moment equation is of degree I, but I guess degree I minus 1. But we know kind of a priori that not all monomials of that degree show up in our equation. And kind of moreover, it's, maybe it's not so hard to kind of come up with examples on your own, but this Bezout bound can be a strict upper bound when these polynomials are sparse. So in this case, this is actually a little bit of more recent work from the late 70s and 80s. And there's a theorem, it's known as this BKK bound. And I could really give an entire talk about this theorem because there's kind of lots of interesting things to say. But I put it here just to show that there actually is a theorem that tells us the number of complex solutions in the algebraic torus, but in our case, that this isn't the variety contained in the torus and the complex variety are actually the same. So this is, not kind of, don't worry about this. It gives us a way to bound the number of solutions for a sparse polynomial system. And specifically, it bounds it by the mixed volume of the Newton polytopes of each polynomial. Now, I kind of don't expect you to know what these objects are, and I'm specifically not, defining them, but I can just maybe say in words briefly that if I give you a polynomial, I can define its Newton polytope as the convex hull of the exponent vectors of that polynomial. So essentially, I've got, n polynomials in n equations, and now I've got a way to associate n convex polytopes to them. Then the mixed volume is a function that inputs, n polytopes, and it outputs a non-negative integer. There's kind of a couple ways to define it, but like I said, that's kind of not the point here is to get too much into the weeds. The main point is to say that there does actually exist another theorem that tells us, it gives us a way to tell us how big our variety is if we're in the situation of a sparse polynomial system. In addition, this bound is also generically tight, so meaning if the coefficients that appear on my monomials, once I fix my monomial supports, if the coefficients in front of those monomials are generic, then this bound will be achieved with equality. The one kind of massive catch with this whole thing is that in general, it's not easy to compute the mixed volume. It's actually sharp P hard. So, this theorem is very nice because it kind of gives us another quantity that's equivalent to, or at least upper bounds the size of our variety. But in general, it's not something that's so easy to compute. But okay. Either way, this kind of answers the first, maybe most fundamental question of, I have a system of n equations and n unknowns, and I know there's finitely many solutions. How many solutions are in my variety? Well, here's kind of two nice upper bounds. But, in our case, we actually don't, we care how many solutions are there, right? That tells us something about the complexity of our algorithm, but we want more. We actually want to find all the solutions, right? So if I kind of give you this moment system and I say, oh, there's 25 solutions, maybe up to symmetry, that doesn't actually help you with our problem of density estimation. So for this, we need something a little bit more. We need this idea, which is known as homotopy continuation. So homotopy continuation is a very broad class of numerical algorithms that seeks to find all isolated solutions to a system of polynomial equations. Now, the main idea behind this family of algorithms is the following. Solving most polynomial systems is hard, but some are really easy. So for instance, if we look on the left here, here's an example of a polynomial system. It's 4 equations and 4 unknowns. And I claim that this is hard. I don't know actually any solutions to this polynomial system off the bat. Maybe if you gave me some time, I could sit down with some, a pen and paper, and maybe we could kind of scratch out some solutions. But, hopefully you can imagine that, this is only a system of 4 equations and 4 unknowns. So as things get bigger, it's really hard to say what kind of any roots of the system would be. Now, kind of in contrast, if we look at the right here, here's another system of 4 equations and 4 unknowns. It's also quadratic. And all the solutions to this system are really easy to find, right? Namely, there's 16 solutions where each coordinate has a plus or minus 1. So the idea behind homotopy continuation is, can I map my solutions from my easy system, the one where I know all of the solutions, to my target system, the hard one, the one that I actually care about? Well, the answer is like, yes, right, of course, you can kind of do whatever you want. But one maybe nice way to do this is to define a homotopy. And here's an example of a straight line homotopy. And then what you do is you kind of start when t equals 0 at your easy system, where you know all the solutions, and then you numerically track those solutions as t varies to 1. Doing this is called following homotopy paths. And the actual way that we kind of numerically follow these paths is typically to use kind of standard predictor corrector methods. So these are methods that are kind of, I'd say, pretty standard in numerical analysis. But the main idea is that you kind of start at some point on this curve. So it's a curve in this little t, and you predict. So you take a step along the tangent direction at some point, and then you correct using something like Newton's method. So I think the kind of best way to think about homotopy continuation is in the following two pictures. So here on the left, this is kind of a big picture of what's going on here. So when t equals 0, these red dots, these are easy solutions, the ones we can just kind of write down and we already know. Then what we do is we slowly vary t and we track these solutions all the way down until we get to t equals 1. We get these yellow solutions. And then these are the solutions to our target system, the ones that we actually want to have. Now, if we zoom in on these red curves, what we see is how to actually follow these curves along. So what we do is we start at some point on this curve and we predict. So we take a step in the tangent direction here, and then we correct down to some kind of epsilon tolerance using something like Newton's method. And so we kind of iteratively take these steps all the way along the red curves. So this is, like I said, the main idea of homotopy continuation. And the nice thing is this is actually a pretty kind of mature area, I would say, of applied math, meaning there's lots of kind of off-the-shelf software that you can use. And these numerical path tracking methods are kind of quite sophisticated at this point. And so my experience is that, they work quite reliably so long as your polynomial system isn't, terribly ill-conditioned. But the one kind of remaining task to do is that I've kind of outlined how to do is how to pick this start system. So if you remember from my example here, I gave you this start system and I said, look, I know all the solutions to this one. Well, that's kind of not enough because there's lots of polynomial systems, right, in 4 variables where I could write down all the solutions to. So the question is kind of how do I pick a good start system? Well, the idea is you want to pick a start system such that the solutions are easy to find, right? This should be kind of clear because otherwise you kind of have a circular problem here. But moreover, you want the number of solutions to the start system to roughly equal the number of solutions to the target system. So if the number of solutions to the start system is less than the number of solutions to the target system, then you have no hope of finding all solutions of your target system, right? Because you get at most one solution for each path tracked. Now, if the number of solutions to the start system is much larger than the number of solutions to your target system, then you have a lot of wasted computation, because essentially you'll be tracking along many more paths than you actually need, or many more paths than will actually converge. And essentially a lot of these paths will just fly off to infinity once you get close to t equals to 1. And so, for this reason, you really want to, ideally you would find a start system where the number of solutions is exactly equal to that of the target system. So this kind of brings us back to the first point here, which is, well, this kind of really hopefully highlights why knowing the number of solutions to your target system is important when designing these homotopy algorithms. So for instance, if your system roughly achieves this Bezout bound, then something known as a total degree start system is suitable. So essentially what this does is it takes each variable and it raises it to the d-ith power, where di is the degree of the polynomial f sub I. And this is an example of the start system I showed you on the first slide. Now, if this mixed volume, i.e. if this BKK bound is much less than the Bezout bound, something known as a polyhedral start system is suitable. Now, in general, I can't kind of write down in a nice prose form what this polyhedral start system looks like, but it's a collection of binomial systems. And kind of maybe more importantly, there exists an algorithm that will find this binomial start system. and then do the tracking. But as I mentioned on the first slide, that's finding the mixed volume of a collection of polytopes in general is short p hard. So maybe you can kind of believe that this algorithm for small polynomial systems, it works very well, but it tends to time out once you get into kind of medium size systems. So it kind of won't be able to find this binomial start system. So there's a bottleneck usually associated with polyhedral homotopy, in which case then you usually just have to switch to the total degree. So just to kind of see one little example here, suppose I wanted to solve this polynomial system f here. So f is equal to the system of 2 quadratic equations and 2 unknowns. Well, a total degree start system would look like the following, because each equation is quadratic. So I have degree 2 in each variable. And you can see here that I would track 4 paths, and this is the Bezout bound of this polynomial system. Now, I was able to run this polyhedral homotopy for this very small system. And here's an example of a start system for polyhedral homotopy. So here you can see that there's only 2 solutions, and that's in fact the BKK bound of this system. So in this case, polyhedral homotopy would only track 2 paths versus the total degree would track 4. So in this case, the polyhedral homotopy is much more efficient. Okay, so that's kind of all I wanted to say on this numerical algebraic geometry and these homotopy continuation algorithms. And now kind of I want to get into the meat of the talk, which is some of the results that we have. But does anyone have any questions on this, these numerical algebraic geometry ideas? Okay, then, for the sake of time, I'll just kind of keep going. So remember, we're trying to do this method of moments for our Gaussian mixture models. Now, I'll say, once you kind of start going through the statistics literature, actually what you'll see is that oftentimes this general case isn't considered. It's kind of, some of these smaller cases are still difficult enough and not well understood enough that they're often studied instead. So there's these 3 special classes of these Gaussian mixture models that are commonly studied in the statistics literature. So the first is where we assume the mixing coefficients are known parameters. The second is where the mixing coefficients are known and the variances are equal. And then the final one is where only the means are unknown. So in each case, we assume that we kind of know more and more about our underlying density. And so we studied all 3 of these cases, and this brings us to kind of our main result. And what this says is that in all cases, these Gaussian mixture models are algebraically identifiable using moment equations of lowest degree. Moreover, we give an upper bound on the number of solutions to each set of equations. So let's just kind of parse this. So let's consider the first case. So in this case, we assume that the lambdas, the mixing coefficients, are known parameters. So we have 2k unknowns, namely a mean and a variance for each component. So we know we need to use moment equations M1 to M2k, and what we are able to show is that actually generically that's going to be enough. That will be enough to get you down to finitely many solutions. In addition, we're able to give an upper bound for the number of solutions because in this case, we can kind of use some underlying geometry and find the mixed volume of those Newton polytopes. And we can verify numerically that this bound is tight for k less than or equal to 8, and we do conjecture that this mixed volume bound is always tight. We then get analogous results for the other 2 cases, as well as giving mixed volume or upper bound on the number of solutions. Then just a note, in the final case, we show that this mixed volume, we can actually show that this mixed volume bound is tight, even though in the other 2 cases, it's just kind of a conjecture. So there's kind of 2 results here. One is this algebraic identifiability for these special cases, and the other of these mixed volume results, so namely an upper bound on the number of solutions. So this mixed volume is kind of what I would say is like kind of the meat of the result. It's the maybe kind of most challenging part. And remember, I told you at the beginning that computing the mixed volume in general is short p hard. So in general, it's difficult to compute this mixed volume. But computing this Bezout bound is very easy, right? We just multiply the degrees. So kind of the long story short is going through the effort to kind of find these closed formulas for the mixed volume, but that's only really worth it if it's a lot better than the Bezout bound. And here you can see in the first case that the ratio of this mixed volume over the Bezout bound, this actually goes to 0 as k goes to infinity. So for large enough k, our mixed volume bound is actually arbitrarily better than what you would get from just applying the Bezout bound. In the second case, this mixed volume bound is always better by a factor of 2. Now in the final case, they're equal, so it might seem kind of trivial, but I'll touch on that in a moment. So kind of one nice thing about these results is that, and kind of what these results indicate is that, say specifically for this first case, that we're going to be much better off using something like a polyhedral homotopy algorithm to find all of these solutions. But as I mentioned, these polyhedral algorithms time out at a certain point. We just can't, the computer kind of can't, it just kind of can't compute a start system. So one nice thing about our results here is our proofs of the mixed volume in the first two cases actually gives a start system that tracks this mixed volume number of paths. So we're able to circumvent the standard bottleneck associated with polyhedral homotopy algorithms. Now, in this final case, this might seem kind of boring because the mixed volume equals the Bezout bound. So like, why go through all this extra effort, But a kind of key point here is that actually oftentimes additional assumptions are made. So namely, they assume that these mixing coefficients are uniform and that the variances are equal. Then in this case, there's actually just a unique solution up to symmetry. So using the techniques of homotopy continuation and algebraic geometry, this problem is actually essentially trivial in this final case. Okay, so that kind of wraps up, I'd say, what I wanted to say about Gaussian mixture models in one dimension. And so in my remaining, like 5 or so minutes, I just kind of want to highlight how all of this can be extended to Gaussian mixture models in higher dimensions. So we want to consider the same exact setup, but instead of the mixture of a univariate Gaussian density, we want to consider the mixture of multivariate Gaussian densities. So again, kind of want to build ourselves up from easiest to hardest. And the first non-trivial case will be when k equals n equals 2. So the mixture of two Gaussian densities in two dimensions. Now, this problem starts to become kind of off the bat more difficult to study. So the first thing is there's no longer a unique moment equation of each order. So for instance, here we have 2 moment equations of order 1, 3 of order 2, 4 of order 3, and so on. So it's just not even clear how to select what moment equations to use. In addition, once you're in 3-dimensional space, it's actually been shown that these moment equations no longer form a complete intersection. So it's not even enough to just select the moment equations of kind of lowest, any moment equations of lowest degree. So it's been shown there's cases where you need to kind of get into higher degree because there's some kind of dependencies among the equations. So kind of all this to say is just once you get into higher dimensional space, it's just not even clear how to write down what polynomial system you care about. Well, now, the slide's been up for a moment, so maybe you can look at this and think, well, some of these equations look a little bit familiar. So for instance, these equations I have highlighted, these will look a lot like the moment equations for a univariate Gaussian mixture model, but just in the variables that are in the top, the first dimension. So the key observation here is that the all 0, except for the tth coordinate moment, is actually the same as the ith order moment for the univariate Gaussian mixture model. This really comes from the fact that the conditional of a Gaussian is still Gaussian. And so what we're doing now is we're conditioning on everything being 0 except the tth components. And so what this tells us is that density estimation for these high-dimensional Gaussian mixture models just becomes multiple instances of one-dimensional problems. And the key advantage here is that we only need to track the best statistically meaningful solution as we go along. So let me just kind of give an overview of what this algorithm looks like. So I input a set of sample moments, and then I output parameters corresponding to those sample moments. Step one, you solve the general univariate case to get the mixing coefficients, the mean, and the variances of one dimension. We then select the statistically meaningful solution closest to the next sample moment. Now that we know the mixing coefficients, we can solve the reduced case to n-1 times to obtain the remaining means and variances. Again, at each step, we'll select the statistically meaningful solution closest to the next sample moments. Now, at this point, we know the mixing coefficients, all of the means, and all diagonal entries of the covariance matrices. And so we just need to find the off-diagonal entries. And while the point is there exists some mixed moments such that the covariances are linear in the other entries, so we can just solve this linear system. So to see what this looks like in an example, we'll go back to a k equals n equals 2 case, and suppose I want to do density estimation for this model. And I am going to give you the following set of sample moments. So this first set I use at the first step, the second ones I use at the third step, and then the final one is for the fifth step. So okay, step one, I use these first 5 moments of this array to solve the general case to obtain the mixing coefficients, mean, and variances. Up to symmetry, there's actually 2 statistically meaningful solutions. So then what we do is we look at what the 6th moment of these parameters look like and compare it to the sample 6 moments. In this case, the first solution has 6th moment 322.75, which was exactly an inputted sample moment. So we would select this first solution. So now we know the mixing coefficients. And so we can use this to solve this reduced system to get the remaining means and variances. In this case, there's only one statistically meaningful solution. So of course, that's the one we select. Now at this point, we just need to find the off-diagonal entries of each covariance matrix. And so we can solve this linear system in the it's now linear in the only unknowns. And of course, we know there's a unique solution. And then we just kind of puzzle piece all of our solutions together. And we'd estimate that our samples came from this density, which in fact they did because I used exact moments, not sample moments. And that's the function of the consistency of this estimator. So that's not by accident. That will always happen when you use exact moments. So just kind of some final remarks on all of this. Steps 3 and 4 can be run in parallel. So once we know the mixing coefficients, we treat each dimension independently. And so we can run these steps in parallel. In general, we need to track, kind of this number of homotopy paths, which looks like a mess in K, but it's actually linear in N. So that means that our algorithm scales, very well in the dimension, although not as well in the number of components. And I'll just say it's even simpler in the cases where some of the parameters are known. So for instance, if you're in the case where you're just trying to estimate the means, but all the variances and mixing coefficients are known, all of this framework can be kind of pushed through, and the algorithm kind of simplifies significantly. A final note is this whole time I've been talking about doing density estimation. And we did do that, but we actually did something stronger, which is known as parameter recovery. So density estimation asks that I find you a Gaussian mixture model that is close to the true Gaussian mixture model. Parameter recovery asks that I find you parameters that are close to the true parameters of the Gaussian mixture model. So it's a little bit subtle, but hopefully you can see in this example the distinction. So up top here, I have the mixture of 2 Gaussian densities with 3 components. Now, for the purposes of density estimation, either one of these densities would be completely fine, right? They're pretty much indistinguishable, except maybe a little bit at the top here you can see. But if we break apart the individual components, so kind of the individual parameters of each density, we can see that they're very different. So for instance, one here has, one component here has weight 1% versus the lowest weight over here has weight 15%. So, for the purposes of density estimation, we can do that, but we can actually do something stronger. Versus with other techniques like maximum likelihood estimation, they can only do this density estimation, not the parameter recovery. Finally, here's just some computational results to show that this does in fact work well and reliably. Like anytime you're using a numerical algorithm, you kind of always have to be careful because things can go absolutely terribly, but that really doesn't happen here. So you can see that the error is pretty much machine precision. And moreover, you can see that the time, so this is the mixture of two Gaussian densities in n-dimensional space. So you can see here that it really does scale pretty much linearly. And I did not parallelize this. I just ran these back to back to back on my laptop. And even so, I was able to do density estimation for the mixture of two Gaussians in 10,000 dimensional space in just over a minute. So, I think that's, quite good. So just to kind of wrap up quickly, we're able to give new rational and algebraic identifiability results for Gaussian mixture models. In addition, we were able to give an upper bound for the number of solutions to univariate Gaussian mixture moment systems. And then we could actually apply these results to efficiently do density estimation in high dimensions. So the paper's up on the archive, and yeah, thank you for your time. I know I kind of ran a bit over, but yeah, I'm happy to take any questions.